Good afternoon, welcome back. This is our 13th lecture, and I am going to title this Asymptotic Bounds, and I think the reason for that will be clear from the last lecture. So perhaps we should just quickly look at the last lecture, and let me zoom out a little bit. So in the last lecture we started talking about we completed our discussion on the Hamming bound. We proved the Hamming bound. We also introduced the Gilbert-Varshama bound, which is a lower bound. In between we said that codes that achieve the Hamming bound with equality are known as perfect codes. So we talked about perfect codes. We also introduced the Golay code as another example of a perfect code, and then we proved the Gilbert-Varshama bound. And then I was telling you, I was trying to motivate you, because the next thing that we are going to do is we are going to take the Hamming bound and the Gilbert-Varshama bound, and then we are going to let n tend to infinity. And I was trying to explain to you why is it that n tending to infinity is of interest, and that is because it gives you an approach towards attaining reliable communication, and which in some sense is the ultimate aim of an error correcting code. Okay. And I pointed out that our approach is going to use long codes, and it is also going to use bounded distance decoding. I explained what bounded distance decoding meant, and then we were in the midst of describing explaining how we would achieve reliable communication. We had started out by looking at the binomial distribution, etc. So we will pick up from there. A very quick recap. We looked at the Hamming bound, looked at perfect codes. This included the Golay code. Then we looked at the Gilbert-Varshama bound. And we were in the midst of discussing an approach to achieving reliable communication. So what I had pointed out last time was that if you feed a code word to a binary symmetric channel whose crossover probability is epsilon, then the probability of k errors was n choose k epsilon to the k 1 minus epsilon to the n minus k. But if n is very large, then this distribution tends to the Gaussian distribution, and this distribution is normal with mean n times epsilon and with variance n epsilon 1 minus epsilon. So, this is the variance. Now, associated with the variance is this standard deviation, which is the square root of n epsilon 1 minus epsilon. The picture is like this, that for large n, the mean number of errors is going to be approximately n epsilon. The standard deviation is going to be square root of n epsilon into 1 minus epsilon. So, the distribution is going to look like this. Okay. So, it is going to peak it will peak, let me draw that a little bit better. So, it is going to peak around n epsilon, and then the standard deviation is going to be on the order of, so somewhere around here you might say that the standard deviation is on the order of let us say root n epsilon 1 minus epsilon. So, the width of the peak is on the order of root n epsilon. Okay, 1 minus epsilon is approximately 1. So, it is like root n epsilon. So, there is a thinning of this distribution as n gets larger and larger, and you might imagine that for very, very, very large n, it is going to look very pointed in between. Indeed, it is going to look something like this, to the extent that you can say, well, the errors, the number of errors is almost exactly n epsilon. Okay. So, you can actually say, so the conclusion is that, so you could say that the number of errors is within plus minus some small some constant times root n epsilon, and we will pretend that that is negligible. So, that you can say that the number of errors is almost exactly equal to n epsilon, and this is sometimes called sphere hardening. So, the conclusion is that long codes make the error pattern more predictable and hence more correctable. And so, part of our approach was using long codes. The second part of our approach was, since there are n epsilon errors, we will use a code of minimum distance d equal to 2 n epsilon. Okay. Now, in practice you may need to make it 2 n epsilon plus some small quantity, but we will ignore that. Now, with this we will have achieved reliable communication. So, you might say, has not the problem then been solved? Not quite, because what Shannon tells us is that given a channel, there is a quantity called channel capacity which governs the maximum rate of information transfer. So, the question still remains, are you achieving that rate of information transfer? Okay. So, let us set this aside for the moment, and now we will get back to our Hamming and Gilbert-Varshama bounds and look at them from the point of view of their values when n is very, very large. So, we will begin with the definition. Given delta between 0 and 1, let d equals n delta, and I take the ceiling function, that is the smallest integer greater than or equal to n delta, and let m n delta be the largest possible size of a block code of length n and minimum distance d. Then define since this is already a definition, let me not repeat myself. Let us just say set R delta to be the lim sup as n tends to infinity of log of m n delta divided by n. So, we are taking the lim sup of this. Now, okay, do not get thrown away too much by the fact that you have this lim sup. Essentially, you are trying to take the limit. The only thing is that it is a technicality that sometimes the limit may not exist, but the lim sup is always guaranteed to exist. And what the lim sup really says is that maybe the sequence does not tend to a limit, but there are subsequences within the sequence that tend to different limits, and we are just going to look at the supremum of all those subsequential limits, and that is guaranteed to exist. Okay. So, this is defined to be R delta. Now, so what the way you should look at this is that R delta is really talking about the rate of a code. So, this represents the rate, and you think of delta as being the fractional minimum distance. And that is why you set, remember we said that we will set d to be n delta. So, that is why you think of delta as the fractional minimum distance. So, in this setting what is of interest is how does R delta vary with delta. Question: how does R delta vary with delta? Or in other words, how does the rate of the code vary with fractional minimum distance? The Hamming bound tells us that m is less than or equal to 2 to the n divided by the sum n choose I. On the other hand, the Gilbert-Varshamma bound says that m is greater than or equal to 2 to the n Now, the way we have written the Hamming and the Gilbert-Varshamma bounds, they are written for any value of n, not just for n tending to infinity. But it turns out that you can simplify these expressions for the case when n tends to infinity, and for large n it can be shown that the Hamming and Gilbert-Varshamma bounds imply that R delta is greater than or equal to 1 minus H2 of delta by 2, correction here, small correction, this should be delta, and is less than 1 minus H2 of delta by 2. So, this part comes from Gilbert-Varshamma, whereas this part comes from the Hamming bound. Now, how does this? I will just tell you quickly in words how you get this bound. Basically, this bound comes from Stirling's approximation for n factorial. You can actually bound n factorial in terms of this h function. So, what is this h function anyway? So, for excuse me, for delta lying between 0 and 1, h2 of delta, or if that is confusing, perhaps I will just call it h2 of theta, so that is defined to be theta log 1 upon theta. So, again I guess I do not want this to be equal to 0, plus 1 minus theta log 1 upon 1 minus theta. And for those who have taken information theory, this is nothing but the binary entropy function. So, this function, if when plotted, looks like this. So, for theta, as a function of theta, it goes up and then it comes down. It attains a maximum value of 1 at theta equal to 1/2 and is 0 at either extreme. Okay. So, here what you do is you interpret this value at 0, you interpret this quantity as 0, because 0 times infinity is still 0, and in that sense, and similarly over here. So, perhaps let me just, with that comment, I will just put this back in, and this is this picture here. Okay. If you use this and plot, you will observe the following. You will observe that what we are plotting here on this axis is delta, and on this axis r delta, and the Hamming and Gilbert-Varshamma bounds, let us hope I can draw this correctly, they give you this bound. So, that is the Hamming bound, and the Gilbert-Varshamma bound is this bound. Okay. So, this is the Hamming, and this lower bound is the Gilbert-Varshamma bound, and you should interpret this, as I stated earlier, as the rate of the code. So, think of it, in the case of a linear code, the rate would simply be the dimension divided by the length of the code, and delta. So, in essence, you are actually plotting something which is like the rate versus minimum distance, except that you are normalizing them by the block length of the code. So, instead of the dimension, you have the rate of the code, and instead of distance, minimum distance of the code, you have the fraction of minimum distance. And what this is telling you is that if you are looking for the best long codes, then the best long codes on this asymptotic plot lie somewhere between the Gilbert-Varshamma and the Hamming bound. So, in some sense, they potentially lie somewhere in this region. Okay. Now, all right. So, we will come back to this plot in just a second. Let us take a look at this expression that we have just written. It tells us that the maximum rate at which you can communicate is between these two. On the other hand, so let me put that down just for clarity. I am going to repeat that expression. So, we know that r delta is less than 1 minus h2 of delta by 2 and greater than or equal to 1 minus h2 of delta. However, if you combine this with our philosophy of saying that whenever we use a code over the binary symmetric channel, we will take the minimum distance to be twice n times epsilon. So, our bounded distance decoding philosophy causes us to set delta, which is d by n, to be 2 n epsilon by n, which is 2 epsilon. So, you can interpret this as saying, because of this, you can actually interpret this as saying that r delta is greater than or equal to 1 minus h2 of 2 epsilon and less than 1 minus 1 minus H2 of epsilon. And once again this comes from the Gilbert-Varshama bound and this comes from the Hamming bound. On the other hand, Shannon tells us that the capacity, so the binary symmetric channel has a certain capacity to transmit information reliably, and Shannon tells us that that rate R is equal to 1 minus H2 of epsilon. So, Shannon tells us that this is the capacity of the channel. So, in fact, instead of R, let me write, let me rewrite that a little bit differently. So, I will rewrite that as R max, which is by definition C, is equal to this. This is what Shannon has told us. Now, if you compare these expressions, let us say that I call this 1 and 2. If you compare these, you will see that in order to operate the channel at capacity, what you need to do is, so you can see that the capacity formula in some sense agrees with the Hamming bound. So, it suggests that one way to approach it is to use a code that achieves the Hamming bound with equality and use your long code philosophy. But it turns out that the problem is that there are no long codes that achieve the Hamming bound with equality. Okay, so, the first conclusion is that our combination of long block length and bounded distance decoding causes us to require the use of long block codes that achieve the Hamming bound to achieve channel capacity. Okay, so, this is just our approach, but the bad news is that in fact, as I just mentioned, there are no long block codes that achieve the Hamming bound, and in fact, what is even more true is that although we have only discussed two bounds, there is another bound which was discovered sometime in the mid to late 70s, around 77, by 4 people from the US, and which actually results in an upper bound which has the following, which is of the following type. Again, I hope I can get this right. So, it is a bound that goes like this. Okay. So, what that tells us, so I think I can improve this figure a little bit. So, perhaps I should do that. Yeah, let us get rid of this. I will draw this more pronounced like this and this like this. So, that is a much better depiction of this. So, this thing here is the Gilbert-Varshama, and this new bound which I have just introduced here is called the McLeese-Rodemick-Rumsey Welch or the MRRW bound, and this is also an upper bound. So, which says that the best codes are to be found in this region. So, this is the region where the best codes are to be found. Okay, I just remembered that that green does not show up very well. So, let us just say that this is the region where the best codes lie. So, our philosophy of using a long code in conjunction with bounded distance decoding fails to achieve channel capacity. And you might say, what went wrong? Well, what went wrong is precisely this. We actually discussed this in our earlier lecture. So, let me just quickly go back to that. So, the bounded distance decoding philosophy is one in which you do the following: you take the received vector and then you look in a ball of radius t. However, you can do better, and we are going to look at that by doing this kind of a thing, where you actually decode to the nearest code word without regard to whether it is in a ball of radius t or anything like that. So, this is actually a better method of decoding, this method here, and our approach at achieving capacity that I just outlined fails simply because we were insisting on doing bounded distance decoding, and in a sense that is the only thing we need to do at that stage. Okay. All right. So, that winds up the discussion on asymptotic bounds. Perhaps it is worth summarizing. So, in summary, we can say that the best codes, we have determined the region where the best codes lie, and this region corresponds to a pair, one being the fractional minimum distance, which is a reflection of the error correcting capability of the code, and the second thing is the rate. Now, you might say, is that all that there is to a code? And the answer is no, because both rate and fractional minimum distance are calculated based on the dimension of the code, which is a reflection of the code size, that is certainly important, and the minimum distance of the code. But the minimum distance of the code only tells you what is the minimum separation between a pair of code words. You can imagine that you would get more complete information if you knew the complete distance distribution of the code. In other words, you knew the distances between every pair of code words. Okay, so, that is another limitation of this viewpoint. But anyway, it is nice to have this picture which tells you where your limits are from the point of view of a minimum distance and the rate. Okay, so that completes this part of the discussion. Next, what I would like to actually look at is other means of decoding a code. So, in fact, we will ask the question, well, supposing I am interested in trying to do the best possible, and by that I will interpret that as saying the one that makes the least number of errors. So, we will call that the minimum probability of error decoder. Okay. So, the minimum probability of error decoder, and we would like an expression for it. So, let E be the event that a code word is erroneously decoded. So that then E complement would be the event that it is correctly decoded. And we want to maximize the probability of correct decisions. Let us look at what that would be. So, the probability of E complement so the probability, I can actually condition this upon the probability that a certain code word is transmitted, and then I am using the total probability theorem to calculate the probability of this event. So, here M is as always the number of code words. So, M is the size of the code, which this expression can also be written as the sum I is equal to 1 to M probability of Ci times the probability that y belongs to Hi given Ci. Now, this may need some explanation, but hopefully not too much. So, the picture is like this. Any decoder whatsoever is going to partition the set of all vectors into regions which you associate with the different code words. And whenever a particular received vector lies in a region associated with a code word, then what you do is you declare that particular code word to have been transmitted. So, for example, here if this y happens to belong to this block where C2 is located, then you will actually declare that C2 was the transmitted code word. Now, you might say wait a minute, you talked about bounded distance decoding and you did not tell us that that was the case. Well, that is true, because what bounded distance decoding does is that it looks within a ball of radius t surrounding the received vector, and if there is no code word within it, gives up. So, that means there are certain situations in which it does nothing. So, when we talk about now, obviously if instead of doing nothing, if you just guess some code word, you would be doing better, because there is some small chance that you might be occasionally correct. Okay. So, the bounded distance decoder is a practical convenience, but from a theoretical point of view, you can always find another algorithm which does the same thing as bounded distance decoding, except that instead of giving up when there is nothing inside the ball, it does something else. So, from that point of view, every algorithm basically boils down to associating making an association between the set of received vectors on the one hand and the set of code words, and this is just an abstract depiction. So, when I actually show you these boxes, I do not necessarily mean that these vectors are contiguous to each other. Okay, this is just an abstract depiction. There is a certain subset of vectors, and when I write Hi here, what I mean is precisely this region over here. So, I am calling this region here as H1, H2 and so on. Now, this of course has nothing to do with the binary entropy function. These are just regions, something like Voronoi regions. So, the probability of a correct decision when the ith code word is transmitted is of course the probability that the received vector lies in the region where you will declare the ith code word to have been transmitted. So, proceeding further, you can actually write this as the sum times the sum over all received vectors. So, here I guess I should remind you that as always y stands for the received vector, right. So, I am going to rewrite this last expression in a different way. I am going to say that the probability of receiving y given C I times the indicator function of h I of y. And what this function is given by I h of z is 1 if z belongs to h I and is 0 else. So, what this does is it just makes sure that you associate with P of y given C I only those vectors y which belong to h I, all right. All right. So, continuing on, this now I can interchange summations, bring the summation on y outside, and I can write the sum I is equal to 1 to m probability of C I times the probability of y given C I and times I h I of y. Now, when you look at this expression here, then you should keep in mind that as far as building a decoder goes, the only thing that is really in your hands, see the probability of selecting a code words, yes, it is in your hands, but most of the time that is determined at the transmitter end. Okay. So, the decoder may just have to live with whatever the transmitter decides to do. So, the decoder does not have control over that. Then the second term, the probability of y given C I, is again something that is not in the hands of the decoder, because that is something that happens across the channel. The only thing that the decoder can really control is this I h I of y, because it selects, the decoder selects the regions h I. So, that means that the contribution, if you allocate y to h I, then that the contribution of that particular y will become precisely this quantity, and you are interested in maximizing the probability of correct decision. So, you would like to maximize this. So, you would like to make an allocation of y to h I if this is the largest. Okay. So, just summarize by saying to maximize the probability of correct decisions, the decoder assigns y to h I if and only if the probability of C I times the probability of y given C I is greater than or equal to the probability of C j times the probability of y given Cj for j not equal to I, and here both I and j. So, this is this. So, then this is the decision rule that is adopted by a receiver that is interested in trying to maximize the probability of making a correct decision. Now, so typically, as I mentioned earlier, now it is typically the case all code words are equally likely, i.e., the probability of Ci is equal to 1 upon m for all I, in which case when you are trying to determine between these two, the probability of Ci now goes out of the picture because it is a constant. So, you decide in which case the probability of correct decision is maximized by selecting y in Hi if and only if the probability of y given Ci is greater than or equal to the probability of y given Cj. Now, a decoder which makes decisions based on this rule is called a maximum likelihood decoder. A decoder that uses this rule for making decisions is called a maximum likelihood decoder. Just a quick comment, a maximum likelihood decoder will employ this rule whether or not the code words are equally likely. Okay. But what we have shown here is that if the code words are equally likely, then the maximum likelihood code word decoder minimizes the error probability. Okay. So, note if all code words are equally likely, then the maximum likelihood decoder will also minimize code word error probability. Okay. Now, there is another comment, which is that we have this greater than or equal to the. So, this might cause some confusion, and you say, well, wait a minute, what if two code words, the probabilities are the same? Then what do I do? And the answer is simple, just flip a coin, choose between them in some arbitrary fashion. Only thing is that your decoder always has to be deterministic, in the sense that given a y, you must consistently decode to a certain code word. You can't afford to say I am going to decode today to y1, tomorrow to y2 for the same receive vector. But when you are designing your decoder and you are faced with a choice, because the probabilities are equal, then you just flip a coin. Okay, but once you flip the coin, then you made your decision and you stick with it. Okay, that's just a clarification. So we'll, and most people just say that explain away the situation by saying in case of ties, one flips a coin, and from that the meaning should be clear. Okay, good. Now, another question that might be in your mind is, wait a minute, when you were talking about decoding and you were describing these regions, you said something about Hamming distance. You said that you might want to choose the regions in such a way that those vectors that are close in Hamming distance would have most likely be in these regions. Okay. So in other words, we have to make the connection between maximum likelihood decoding, which after all does the best that you can hope to do when the code words are equally likely, and what you intuitively want to do is decode to the nearest code word. Okay. So we will just state that as a lemma. I am not sure we will have enough time to prove it today, but let me just state it, lemma over a binary symmetric channel, maximum likelihood decoding reduces to minimum distance decoding, which we will write as MDD. So, the proof, let the Hamming distance between a y and a Ci be d, then the probability of y given Ci is epsilon to the d 1 minus epsilon to the n minus d, which you can write as 1 minus epsilon to the n divided by 1 minus epsilon to the d. Now, if epsilon is much smaller than 1, then epsilon upon 1 minus epsilon will be less than 1, which will imply that the probability of y is maximized by minimizing the Hamming distance between y and Ci. Okay? And that is the connection. So, we will pick up on this. I might repeat myself a little bit next time, and then we will actually expand this into a complete decoding algorithm, which is very simple and which does exactly this, minimizes the probability of error, and in that sense which is an optimum decoder, right. So, let us stop here. I will recap and continue from this point onwards in the next lecture.